Hi, I'm Jack Buffington from robotbrigade.com. This is a video in a series of videos about a mapping robot that I have created, and in this one I'm talking about the electronics that I designed for this. I'll go through the circuits and describe exactly what they do and why I made the choices that I did. I'll also talk about some things that I wish I had done a little bit better. So right here is the circuit board, and this one's obviously an unpopulated one. I have designed it so that you just assemble it at home. I have personally used a reflow oven. However, it's quite possible to maybe hand solder, but definitely if you use I have used an electric griddle in the past. The trouble with the electric griddle is sometimes your board will curve up a little bit and you don't get the melt quite as good, so you're pushing down with the screwdriver to make it touch. But you know, in a pinch it works, and you can go out and get one of those at Walmart for next to nothing. Anyway, let's switch over to the computer and go through what's going on with the circuit. Okay, here we are in the schematic for the circuit board. Overall, it's pretty simple. I have it all on one page. It's maybe not quite as organized as some people might like, but it is a functional circuit. Let's start with the power section. So one of my goals with this project was to have the robot be able to control its own power. So you didn't turn it on and off totally manually. I have it so that there's a button which is connected to right here, and what it does, I should explain, I have actually two buttons, and that's because I wasn't sure that I can get a connector of the right size for my circuit board, so I hedged my bets and put in a second one with a slightly different pin spacing. Anyway, I wanted to be able to leave the battery in at all times, and in order to do that I needed to have extremely low current draw when it was in the off state. And so I've used this chip here, the LTC2954-2. Definitely don't get the -1 version. I've made two versions of this circuit board, and the first one I had a -2 in the smaller part, in the smaller package for this chip, and I figured that's just a little too difficult for people to solder, so I went to a slightly bigger version, but I got the -1 version, and it of course didn't work the same way. So once I figured out and went back to the -2, everything was working again. But what this is it's a chip that lets you control the power to a circuit using a MOSFET. It draws extremely low current, and when you push the button it will turn on the power. After that, if you push the button, it has a I believe it's this line, the interrupt line. I have this going back to my microcontroller, so I can also use that same button as input. And specifically I've got it so the number of times that you press the button is sent back to the microcontroller. So I could do 1, 2, and then the microcontroller gets 2, which then gets passed on to the ROS node. Anyway, if you push and hold for a certain amount of time, which I believe is controlled by this capacitor, then it will force kill the circuit. So the first thing that I do is I have this MOSFET here applies power to a 3.3 volt out, which goes to my microcontroller, but it also is going to, I'm calling it 21 volt rail. I think the maximum voltage of this battery is about 20.5 volts. One important feature is this diode right here. At first I did not have this in my circuit board. I figured it's not necessary. You know, I have the terminals labeled, and it's no big deal. Of course, I was talking on a phone like an idiot when assembling my first revision of the board, and wasn't totally paying attention to what I was doing, and I hooked up power backwards. And so that was rather upsetting. So I put the diode in so that can never happen again. That's about all I have to say about that. When the 3.3 volt rail is on, this little LED right here turns on. Then I have two DC to DC converters. This is just sort of a drop-in module. It's maybe a tad on the expensive side, which drives up the price of this board, but it's definitely easier than designing my own switching regulator, which I have done before. And basically, I have one regulator for the CPU, which would be my Raspberry Pi. I have another one for the motors. I've found in the past that you definitely don't want your microcontroller or CPU to be on the same supply as your motors, because motors produce a lot of noise which can interfere with the proper functioning of a microcontroller or CPU. Over here I have a voltage divider that is used for battery monitoring, so I can monitor the voltage of the battery at all times using the microcontroller. I have a speaker here. I'm currently using it sort of just as a beeper, but it is a full speaker, and I could presumably drive it with a wave file or something. I've decided at this moment I'm not going to expend the effort and have stuck with just feeding it square waves. I have an optional servo header here, just in case I wanted to tilt my LiDAR unit on the top of this. I have three or four, let me look at the board here. Yes, I have 4 I2C ports. I2C is also shared by a EEPROM that the program for the microcontrollers is stored in. I have a serial port that is used to go to the Raspberry Pi. Finally, over here is another serial port that's primarily used for programming, but I can also debug to a serial console on my computer, which is kind of handy. Down here I have an auxiliary header, which I am using currently just one pin of that to detect whether or not the CPU is on. So if the CPU turns off, it detects it and it turns off the whole system power then. The microcontroller has a kill input right here that when it is driven low, it causes the whole system to turn off. This chip does that. I should also say I have right here I have a little indicator LED for 5 volts for the processor as well as 6 volts for the motors. I currently have encoded motors on this robot, but it is not absolutely necessary. If you look at the Pulau, what do they call that? The 3Pi robot, it has really good motor control in a open loop manner, and it's because they are using a switching regulator to drive the motors. I was really impressed by that. I had always previously driven the motors on my robots with just straight from the battery, and the trouble with that is you can't do precise turns and things like that, because as your battery draws down, the voltage sags, and so you won't turn quite as much if the battery is low. But with the switching regulator in here, even if we weren't using encoded motors, then you would still get reasonably good turns, or you would reasonably know I've moved about a meter. So let's see. I have two headers here for encoders, one for each of the drive motors. And I have four PWMs. These are for driving the H-bridge, which is a L298N H-bridge module that you can get on eBay or Amazon for very little money. I highly recommend using that unless you need to go higher current. Otherwise, pretty much everything coming out of here is just signals to these other things that I've talked about. This is one possibly controversial decision that I made, and that is that I am using the Propeller microcontroller. I'm using the Propeller 1, and it is a oddball of a microcontroller in that it doesn't have interrupts and it barely has any peripherals, and it has 8 cores. It's a 32-bit microcontroller. It has 32K of RAM, and I really like it because the way that you use this is you task a core to be something like your motor controller or a pulse width modulation generator. This microcontroller is super flexible. If I were to use something from a PIC or AVR line or some sort of ARM, then the pinout's going to be pretty constrained based on, okay, well, the serial port connects to pins 10 and 12, or sometimes it could be 13. But also 13 is used by SPI 0, and you know, if you want to use those, you're constantly juggling this around and it makes board layout difficult. But with the Propeller, you just say, you know what, I'm just going to write my code so that the PWMs are all right here. But I could easily move them over to these pins or these pins. It doesn't matter. Every pin is general purpose with the exception of these 4 right here are sometimes used for the boot of the program is uses pins 28 and 29, and programming of it uses 30 and 31. But as you can see, I'm using these same pins for my other I2C things, which one of them is the OLED display. At some point I'm probably going to add a I2C based rangefinder to the robot so it doesn't accidentally drive over the edge of my stairs, but I haven't added that on yet. So anyway, yeah, I really like this processor. It makes sense if you're doing one-off or low quantity, or you're selling it for such a fantastically huge markup that it just doesn't matter that you get every dollar and cent wrung out of the price. You know, if you're producing something in 100,000, this is not the processor for you. But if you're doing something in quantity 1 or, you know, maybe up to 50, then this may be better. There's so much code out there, it's just super easy to use once you get over the hump of assembly language programming, I should say. But, you know, I really get into these kind of things, and so that doesn't really matter to me. I'm going to switch over now to the board layout, and we'll talk about that. Okay, so here is my board layout. You can see up here prominently. If I were to make another version of this, I have found that this diode right here is a little too small, and I cannot see easily which way it needs to be oriented. Let's just talk about the various things. So I have battery power coming in here. I have the CPU power coming out here. The motor's coming out here. Here is the, I believe it's the 5 volt. Yes, the 5 volt switching regulator circuit is here. The 6 volt switching regulator is here. One thing that I don't like about this board also is I decided to put my power indicators here, which is fine if you're looking straight down on the board, but as it is in the actual robot, I think it would be better if these were over here and here, because you can't really see them when you're looking in this way. Likewise, I think here's my 3.3 volt indicator. It's not super ideally located. And I also have one small LED that's a user LED. I always like to have one LED just to help with debugging. And I have that right here. It's not so big of a deal if I'm debugging and I have the robot opened up, but if I did need to use that for something, I think having them all over here with nice little labels for what they are would be better. The servo, which I'm not currently using, is over here. The power button right here. As I mentioned before, I have two different buttons that could be attached. I believe I used the larger of the two. Let's talk about the connectors here. I used JST PH connectors, I believe. Let's highlight one of these. Yeah, it's a PH series connector, and I've been finding that these are tricky to get. And I don't know if it's because I've been designing this in a pandemic or they are just generally tricky to get. I got all of mine by buying a parts assortment that may be a Chinese knockoff. I'm not sure. But they've been working fine for me. I think if I were to design this again, I would try to find some other parts series that has more availability. Here is the Propeller microcontroller. I believe that this right here is my analog to digital conversion circuit, which I didn't point out, but this is using sigma delta analog to digital conversion. This is the first time I've used this, and I gotta say it's remarkably linear. I thought that there would be a lot of non-linearity to it, but I can calculate my battery voltage to within 1/100th of a volt, so, or maybe 3 or 400ths of a volt. So it's been working great, and that's plenty sufficient for what I'm doing. I suppose if I integrated for a longer period of time, I could achieve better, because sigma delta allows you to vary the number of bits. This is the EEPROM for loading the program to the microcontroller. Over here, I believe this is the major MOSFET that turns on and off the power. Here is the chip that LTC 5940, I believe it was, that is the main power switch chip. Here are your I2Cs and serial over here. For whatever reason, I could only find a very large 5 megahertz crystal, but didn't really matter. I had plenty of board space. I have used much smaller ones in the past, but I guess I was just a little too lazy to find a smaller one. So all in all, that's the circuit board here. I ordered mine from, I think, PCBWay, and got it back. I also bought a stencil, and for those of you who are not familiar, I am not going to have a video of this in this series, but it is super easy with a stencil to populate a circuit board. You just tape a couple circuit boards around your circuit board so that everything's nice and flat. Lay down some solder paste and use a credit card to squeegee it over, and where the holes in the stencil were, you get a nice pad of the solder. And then what you do is you just take tweezers and you stick all your parts down and put them in a reflow oven, or as I mentioned before, a electric griddle, and just run the cycle, and you have a almost completely good circuit board. Sometimes for some of these smaller parts, I stuck to 0805 components because they're easier to work with, and I have a stock of just about every value you could possibly think of. Sometimes these will do what's called tombstoning, where this side maybe didn't stick, and it rises up and stands on end on this pad. And so you might have to go in there and touch that up with a soldering iron, but it's way easier than soldering the whole darn thing. Yeah, maybe at some point in the future I should do a soldering video, but there's other videos out there by other people. I suggest you watch those. So there you go. This is the electronics for the mapping robot. For robotbrigade.com, I'm Jack Buffington.